So here's a quick problem from chapter 11 in Serway. It's one of these turntable type problems. You've got a woman, who you know the mass of the woman, standing on the rim of a turntable, and you know the moment of inertia of the turntable and its radius. And the turntable is able to rotate around a frictionless axle. The woman then starts walking in a clockwise fashion at some speed, so W I'll denote as the woman's speed, 1.5 meters per second, relative to the ground. Consider the woman turntable system as motion begins. So as motion begins, this is our system. And we're thinking about what is conserved and what is not conserved for this system. So part A is the mechanical energy of the system constant. The answer is clearly no, because initially the kinetic energy is 0, but finally the kinetic energy is not 0 because the woman is moving. Where's that energy coming from? The woman is expending energy, right, in her muscles. She's converting chemical energy into kinetic energy in order to propel herself forward, right? So mechanical energy is not being conserved here. We have some external input of energy from the kind of muscular expenditure of energy by the woman. How about the momentum? Is the momentum of the system constant? The answer is also clearly no, for the same reason, because we have P initial is equal to 0 when the woman's at rest, and P final is not 0, so because the woman is moving, right? You might take a moment to think, how is it possible? When is momentum conserved and when is it not conserved? Let's go back to Newton's second law. The sum of the external forces on the system is equal to its rate of change of momentum. That's one way of writing Newton's second law. It's a fancy way of writing F equals ma. If the left side is 0, then the right side must be 0. So we would have Pi equals Pf. If you don't have conservation of momentum, which we don't have in this case, that means that the left-hand side must not be 0. There must be an external force on the system. Where is the external force? If you think about it, imagine this turntable was sitting on an ice rink. As the woman walked forward or upward in the north direction, the table would slide backwards in the south direction. Because it's not going to do that, there's something holding the table in place, and of course it's this axle here, right? So the axle provides an external force. And that force causes the momentum to not be conserved. Okay, let's go on to the next part of the system. So for part C, we want to know, is the angular momentum of the system constant? So you have to ask yourself, under what conditions is angular momentum constant or not? So we need our Newton's second law, but for rotation. It looks like this. External torques acting on a system will be dl dt, where L is the angular momentum of the system. If the left side is 0, there's no net external torque on the system, then the right side is 0. So that means dl dt, there's the rate of change of angular momentum is equal to 0, meaning that Li is equal to Lf. And you can see that that is the case here because there's nothing that could exert a torque on this system other than the axle, right? The axle is the only thing that's touching the system. So the axle keeps the thing from sliding, but it doesn't have any friction which can change the rotation. So it's a frictionless axle, and so that means that the axle exerts no torque. And so we have Li equal to Lf. And then in moving on to part D, in which direction and with what angular speed does the turntable rotate? Now we're going to use the principle of conservation of angular momentum here to answer that question. I guess I forgot my vector signs there. So let's apply the conservation of angular momentum to answer part D. So in the previous part of the problem, we already argued that there's no torque on the system being the woman and the turntable together. The only thing that's sort of interacting with that system is, well, gravity, but gravity is not going to change any rotation in this horizontal plane. And then that axle, but the axle is frictionless, so it can't change the rotation. And so we have Li equals to Lf. Initial angular momentum is equal to the final angular momentum. Remember, the woman has some speed here. So let's apply this. The initial angular momentum is 0 because woman's at rest and the table's at rest. And then we have here the angular momentum of the woman plus the angular momentum of the turntable is equal to 0. All right, what's for L, I'm going to use I omega. So I'll use moment of inertia of the woman times omega for the woman plus the moment of inertia for the turntable times omega for the turntable. Now the woman we're treating as a point mass, so we know the moment of inertia for a point mass. It's going to be like this. Mass of the woman times r squared, omega woman. And then I'll just leave the moment of inertia of the turntable because we know that, omega of the turntable. So finally we can solve this for W for the turntable, omega for the turntable. Okay, so let's take a second and look at this equation. You notice there's a minus sign here, and the minus sign is an equation with vectors, meaning that the vector for omega for the turntable is in the opposite direction of omega for the woman. And omega is an angular velocity, so what it means is that the table will rotate in the opposite direction that the woman is rotating, right? So the table will rotate, the woman is moving clockwise around the circle, so the table will rotate counterclockwise. The woman's angular momentum or angular velocity has to do with a clockwise rotation. To keep the angular momentum constant, the table has to rotate in the opposite direction. Let's think about the magnitude. So the magnitude, then I can disregard this sign. These are all positive numbers. And to get the magnitude of the angular velocity of the woman, I'm going to use V of the woman is equal to omega of the woman times r. So let's substitute that in. Mass of the woman, r squared, it, and omega, I will put in the speed of the woman divided by r. Now one of these r's will cancel with one of those, and we've got our final formula here. So there's your final formula. We know all those numbers, so let's plug in the numbers, check the units, and that'll give us our final answer. So there are all the numbers. Let's check the units. Kilograms cancels here. I've got 2 meters on the top and a meter squared on the bottom, so I'm left with 1 over seconds. This is an angular velocity, so radians, remember, radians can kind of appear and disappear in calculations. So I can put in the radians by hand, and I get here equals 0.36 radians per second, and we already argued that it was counterclockwise motion. So there's the answer to the problem, a kind of simple conservation of angular momentum problem. We just argued that there was no external torques on the system, meaning the angular momentum was constant. We used I omega for each of the angular momentum, of each piece of the system. And then remember that depending on what it is, they have different formulas for I. So the angular momentum for a point mass is mr squared. The angular momentum of the turntable, it would be a disk, so 1/2 mr squared, but in this case you're just given the number for IT. So these kinds of problems show up a lot where you're kind of conserving angular momentum as someone walks around a turntable. So now you have some experience with this kind of problem.